Hello and welcome to Func Prog Sweden number 8. And first up, I would like to welcome all recurring viewers. Thank you for coming back to our meetup, Func Prog Sweden. And to all new viewers or first-time watchers, welcome to Func Prog Sweden. This is the meetup where we explore functional programming and functional programming languages. And today we're not just going to explore a functional programming language. So I'll head over to the agenda. Today we are going to get an introduction to functional programming in Go by Carsten. And on the second topic, we'll do ChatGPT as your Erlang coach by Georgiana. It's going to be a very interesting meetup today. First up, I would like to thank our video sponsor, Otherbeat. Otherbeat is an IT consultancy company focused on functional programming. If you want to know more about Otherbeat, check them out on otherbeat.com or on social media. And the coming schedule then, we'll do another meetup, of course in December, and then another one in January, and then in February. For January and February, we haven't set the dates yet, but we'll come back with that and announce them as soon as we have presenters. And if you want to support the Func Prog Sweden community, you head over to Meetup and join the community. And you hit subscribe somewhere here on the subscribe button for our channel. And if you have questions, want to talk to other people, what is functional programming all about? Head over to the Discord channel and you'll find all the links and everything in the About section. If you have questions during your presentation, please ask them either in the Discord server or here on the YouTube chat. With that said, let's get started. Our first presenter, Introduction to FP-Go, Functional Programming for Golang by Carsten. Welcome, Carsten, to Func Prog Sweden.
Hey, my name is Carsten Leue. I've been a software developer for IBM for around 20 years now. And recently we have published an open source library with the Apache 2 license that introduces that makes functional programming available for the Go language. I'm actually feeling very honored to have been invited over to the Func Prog Sweden meetup to talk to you about this library. And I would be very happy to engage in some discussion about this library at the end of this presentation. So what we will talk about. First, in this presentation, I would like to motivate why it makes sense to have functional programming for Go. Go, in the first place, is an imperative language. It is designed to be an imperative language. So why does it make sense to use functional programming concepts in this imperative language, and why does it help to have a library to support you doing so? In the second part, we will have a closer look at how Go code using this functional extension, I would say, to Go looks like. Go code that uses this FP-Go library. We'll delve into some of the concepts that the library has to offer. And again, we'll have a look at code. It will not be a complete in-depth investigation into the library. I would like to concentrate on some of the aspects to give you some motivation to look at the library if you find this helpful. I would like to conclude my presentation with some performance considerations and a quick discussion on my view on whether it made sense to introduce this library, and a couple of thoughts about this. So this library has been published and open sourced by IBM with me as the maintainer of that library. But I still want to make sure that in this very presentation, I am presenting this as an individual, and there are no obligations whatsoever with respect to plans or for the future of this library that you can derive from this presentation. Just a legal disclaimer. And I would also make sure to mention that the library FPGO has largely been influenced by the awesome TypeScript library FPTS by Giulio Canti. So this is a library that brings functional programming concepts to TypeScript into the JavaScript world. And at least to me, even after so many years of software development, it has been a revelation on how the application of functional programming concepts in JavaScript, which I've used for a long time before finding this library, how this library made it easier and more concise to write TypeScript code. The actual bait for me was this IOTS library, which is a dynamic type checking system for TypeScript. If you work with TypeScript or JavaScript, I recommend to make sure to check these libraries out. And you will find that the FPGO library is largely influenced and follows many of the same concepts as this FPTS library. As a starter, I would like to talk a little bit about my personal journey to functional programming. I mentioned that I've worked for a long time, more than 20 years, in software development. I'm actually a physicist, and after my PhD in physics, I have decided to turn my passion for coding, which I've always had since my youth, so to say, to turn this into a living, and I joined IBM around the year 2000. And during my career, I've worked as a software developer, as a software architect, in changing roles on a large set of very interesting and challenging projects. And this timeline is supposed to show a bit what programming languages came across my way. It started with the development on a large-scale portal server system around the year 2000 for like around 10 years. And at that time, a portal server had to be implemented in J2E. That was the platform of choice, and the language of choice, of course, on J2E is Java. We developed both backend and frontend. Frontend, that was the time when this term Web 2.0 came up. So when the JavaScript portion of the application code became more and more relevant and important, which led to experience in client-side frameworks for the client-side UI layer. And the frameworks I've worked in was Angular, which introduced me to TypeScript, and React, which introduced me to a couple of very interesting programming patterns. But both frameworks have in common, they are both JavaScript-based in the end, and client-side. And JavaScript, of course, is also like a language that's been mandated by doing front-end coding, because it has to be JavaScript to be run in a browser in the front end. So after the experience in the portal server world, we developed a content management system based on microservices. And these microservices were coded in Node and partially in Java. The languages of choice, in this case, JavaScript for the Node, or TypeScript for the Node version, was due to this good scalability in the microservices world of TypeScript and Java, because the team was just proficient in Java. And so we used Java, and we used like Vertex as a framework there. More recently, I've been more involved in mainframe applications, secure applications, and also applications that got integrated as cloud services into the IBM cloud. And the languages of choice in this area were Python, Go, Rust, and TypeScript again. Python, because the team was proficient in Python. TypeScript, basically in this case for testing purposes, and Go, which is the reason I'm giving this talk now. Go, because the cloud community is dominated by Go, I would say. many of the large-scale libraries, frameworks, and solutions are implemented in Go. And if you want to integrate with these libraries, then you better do it in Go, or it's more complicated. For example, if you want to integrate into Docker, or if you want to integrate as an operator into a Kubernetes service, then the ecosystem and the libraries of choice are coded in Go. And again, this is what led to the development of this library. You might have noticed that the languages of choice during my journey here, they are all imperative languages. And so I've also thought about what's the reason for the choice of languages, actually. And it turned out that in most cases, there were non-functional factors, I would say, for the choice of language. Either it has been a platform requirement in the J2E case, there was just no option to implement a portal server in a different language other than Java. Sometimes you need to integrate into existing ecosystems. It's the team's skill set that dominates the choice of language, or it's industry trends. But in any case, in all cases, the decision for the language had not been dominated by features of the language, such as functional features of a programming language. We rather pretty much had to stick with languages for different reasons. And of course, over this long time in development, there's some key aspects that occur to me that were always challenging in my experience, independent of the actual language we were working in. Sometimes languages made it easier, sometimes harder, but I always stumbled across these aspects. And first of all, the testability aspect of a solution. In many cases, projects are driven on a tight schedule. Time to market is a really important aspect. And this can lead to code that is not as testable as you would want it to have. Let's put it that way. For example, in an ideal world, you would have a code that is completely covered with unit tests. With unit tests, then you would write integration tests and get a coverage as complete as possible. But it turned out that it's really easy, and I would say it's easy in imperative languages in particular, to write code in a way that it is not easily testable. For example, it's very easy in imperative languages to add side effects to existing code, such as updates to shared state, or reading, writing to external sources such as databases. And as soon as you have that intermingled with your code base, then it's hard to write a unit test for such code, because you never know if there's an ordering dependency in your test case, if it alters a shared state, or if your databases or your backend systems have to be set up in a particular way in order to make your function testable. This is all solvable, either using mocks or using setup functions. But this makes the development of test cases difficult, more difficult than it needs to be. Another aspect, and that is related to shared state, I would say, and the intermingling of different aspects in the code you're writing, is the ability to refactor code. If your code changes some shared properties of the system, then you never know if you can factor that piece of code out, because you do never know if other code depends as a side effect on these modifications of shared state. Race conditions, of course, are also a problem if you consider shared state. And it boils down to really basically to state management. And I would say, in hindsight, well, let's put it that way. Of course, not all code suffers from these deficiencies. It is very well possible to write code that is testable in a good way in imperative languages. And in hindsight, it turned out that much of that code followed principles you would also find in functional programming. And this is what actually motivated me to look more into the realm of functional programming to get a better sense of the abstractions that also helps not just in functional languages, but also in languages that are imperative in nature and that just lead to better code. And on this slide, I have summarized a couple of aspects of functional programming that I find very helpful. Of course, this is not a complete set, but these would be my favorites. The idea of pure functions, of course, like a function that produces the same output just depending on the input, that doesn't have any side effects, it doesn't modify input parameters, shared state whatsoever. It could in principle be replaced by a lookup table. But such a function, of course, is an ideal. It is very well testable, and the attempt to structure your code base with pure functions leads to reusable and very testable code. The second aspect is the idea of composition, where instead of dispatching calls to other functions from your function, so you would create a tight coupling between functions, you would structure your code as pure functions and move the layer to move the ordering of calling these functions out of the function by composing them using well-known and standardized composition functions. And we'll see this in an example later on. I mentioned before that in the testability argument, one of the main problems are side effects. So side effects in the sense that you modify either shared state or you read-write from an external system. Because as soon as you introduce a side effect, you never know if there's ordering dependencies and you have non-reproducible effect on the function. But in reality, every meaningful program has side effects. I've not encountered a single problem where side effects would not be needed. You typically have to talk to different systems. You have to perform I/O. But what makes side effects manageable from a functional programming perspective is the idea to model them in a specific way, to model them as managed side effects. And so you can clearly identify a function that has a side effect and tell it apart from a function that does not have a side effect, that improves on readability and the ability to reason about your code. And it also makes it possible to first compose your program in a pure way and then apply side effects only at the very end of the cycle. And this, to me, is a very good way to deal with side effects in a functional world. Immutability is another key aspect. Typically or often in imperative languages, you find that data structures are mutable, and often this is done with the argument that then the performance of the overall performance of the program is improved, because some algorithms can be implemented much more efficiently on mutable data structures than in immutable data structures. However, as soon as you have mutability in your code, it's much harder to reason about this, to understand side effects, to understand the effects of refactoring. So introducing immutability wherever possible, even if the language does not enforce that, is a great value in my eyes. And last, I have it here as map filter reduce. I could extend the list. The idea is that there exist quite a number of concepts, of abstractions such as the map filter reduce pattern. I could add here chain, applicatives, whatever, that are common across different types of data structures, such as arrays, records, ethers, whatsoever. But so you have a set of common monadic functions that can be applied to a huge variety of data structures. And as soon as you understand the logical concept of these functions, no matter what data structure you apply to, you understand the effect on that data structure. That makes code that follows these patterns very readable, and in my experience, much more readable than code that is not using these patterns. So that's, and if I had to choose two of these features as the most important ones from out of the functional programming world, I would say the ability to tell apart managed side effects from pure functions is one of the key features, and the attempt to handle data structures as immutable as possible is the second one that I would find the most valuable. So then, why have you selected Go for this library? Go has been designed to be an imperative language, explicitly not to be a functional language. But as I motivated in the very beginning, sometimes the choice of language is not determined based on the features of the language, but because of the ecosystems of the libraries you have to interact with. And Go has quite a bit of pluses on its side. It has a huge ecosystem of libraries that you can interact with. For my work, we often need good crypto libraries, so it has very good implementation of these crypto libraries. It has, I could say it has a library for everything. So a huge and very well reusable ecosystem that you can interact with. Also, I would say it has a really good concurrency model. Concurrency in a programming language is also important if you deal with server-side languages, because you want to be able to handle many requests in parallel. You want to potentially make different requests to outbound systems. And ideally, you want to do this in a concurrent way. Traditionally, such as in Java, concurrency is modeled as threads or even processes, which are quite heavyweight. Go has the model of what they call Go routines, which is something like, maybe you've heard the term green threads for that. It's basically a concurrency model that is modeled by the Go runtime on top of operating system threads, but in a way that the overhead to spawn such a Go routine is very small. So the idea is that you can have like thousands or even tens of thousands of these Go routines, maybe not tens of thousands outbound connections, but at least Go routines that run logically concurrently, of course not in parallel. And the runtime takes care of that. So that is very convenient. Another key feature for us is the compiler toolchain. It's really easy to get started with Go and to compile and run binaries. There's no complicated library setup. It's all integrated. You basically initialize your Go module, you get your dependencies, and you can compile it. That's really a no-brainer, and it works really stable and really well. And one of the side aspects of this that is very important, or that is very useful, is the fact that the binaries that are created by Go are fully self-contained. There's not even a dependency on the C library, as you would normally see in compilation results. The reason is that the Go development team has decided to implement even low-level functions, not against the C library, but directly against the kernel functions. So you basically have a zero dependency binary. The only dependency is the dependency on the kernel. And that makes it easy to transfer binaries between systems, to install them. You don't have to be worried about version incompatibilities of dependent libraries or whatsoever. Another aspect, in particular for us in the mainframe world, is that Go supports cross-compilation in a really convenient way. So you can develop your code like on an x86 system and then cross-compile it on the same system to different architectures and then just run it there. It's all integrated and it's again a no-brainer setup. And the last part is compilation is fast, which is good during development time, and it's very well integrated into IDEs. Right, so these are all aspects in favor of using Go. And of course, non-functional constraints, because we need to integrate into Docker, Kubernetes, Terraform, whatever. You better use Go as your language of choice. But I don't want to hide that there are also reasons why you do not want to implement functional programming in Go. And one is the designers of Go have clearly designed Go to be an imperative language. And that leads to like a guide of idiomatic Go style that they suggest, that the Go designers suggest you follow. And this idiomatic Go style is not necessarily what looks like functional code. So if you integrate maybe into an existing Go project with code reviews that enforce idiomatic Go style, then maybe this library is not for you in this case, because at some places, and I will discuss in which ones, it does not follow the idiomatic Go style, but it implements a functional style for reasons I think make sense, but which are not meant to be implemented that way by the Go designers, Golang designers. And then third, I would say a key feature of Go that makes it possible to write this functional library, this FBGo library, is the concept of generics. Generics is the term in Go for type parameters. Instead of having hard-coded types, you can make the type itself a parameter. That's what they call generics. Generics had been added to the Go language relatively late, just in the beginning of 2022, and the type system is still evolving. So it's in no way comparable, in my eyes, to what Haskell has to offer. But it's still very useful. But it also puts constraints in what we can do in Go. And we'll discuss this on the next slides. On the flip side, there are also some features in Go that are functional programming friendly and help with writing functional style Go, I'll say it that way. Again, generics. This is one of the key enabling factors. And it had been added to Go in 1.18, in version 1.18 in 2022. Other Go features that are helpful in this area are the ability to write higher order functions. This means you can write functions that return other functions. Functions themselves in Go are just objects, data structures, just like any other data structure. Just like a struct, a pointer, an integer, whatever, you can assign them to variables, you can pass them around, or you can return them as the result of other functions. So this is very helpful, and the FBGo library makes quite a bit of use of this feature. Closures are also very important, and this is also fully supported by the Go language. Closure means that the parameters on a function that returns another function are captured in that other function. I will show an example later on. So as a summary, functions are first-class entities in Go, and that is extremely helpful, like writing functional code and developing this library. And of course, the strong typing aspect of Go. Go is a strongly typed library. in contrast like to JavaScript or Python or whatever. And having strong type constraints gives you the confidence, gives you a lot of confidence that your code is okay, just by looking at the types. It also makes it much easier to understand an existing function. If you look at the function declaration, you understand the types of the declaration, and with the idea in the background that we follow a functional style and that functions like are pure, or if it's an IO related function, then it has a special syntax. You can immediately make out from the signature of a function what it's supposed to do. And this is supported by a strong typing feature of Go. So let's have a quick look, just as a really 10 seconds introduction into the Go syntax, how this looks like. Here in this example, we have two functions, the add-ins function and the add-numbers function. And the first one with the integers uses explicit typing. First you see every function starts with a func keyword, then the name of the functions, then the parameters, and each parameter has to have a type. So we have two integer types, a return type of int, and we just compute the sum here. Prior to the introduction of generics in Go, if you wanted to have the same function for, say, not ints, but floats, or doubles or whatever, then you would have to write a different function explicitly using int, float signatures, or you would have to do type introspection using a generic like any or interface type, which of course is not ideal if you want to have type safety. With the introduction of generics, which you can see in the second example here, we can make the actual type a parameter, a variable of the function, and we do this in these square brackets after the function name. We see that we have introduced t as a type constraint. Then we can use t across our parameter definition and our return type. And the part after the t is a restriction on the possible types of t. In this case, it's restricted to be of a number type. This number type comes actually from the FBGO library. It's basically a union of all types that have the semantic of being a number. I think in the meantime, it has also been introduced in the Go base library, but at the time of writing, it had not. So this basically says you can call this library like with an integer, float, complex number, whatever. And the logic of building the sum, of course, is always the same. At compile time, the compiler will compile this into an explicit version of the function. So at compile time, the compiler needs to know what is t, what's the value of t, and then it will produce the correct implementation for that value. So if you use the same function for int float, you will have two versions of this in your binary at the end. In my second example, I have an example of how a closure looks like in Go. You can see this here in capture value. Again, we have we see that this works very well together with generics. In this case, t is again the type parameter, but it's not constrained. It has the any type. And just for the fun of it, I have basically created a function which a captured parameter, and it returns another function. You can see this, the return value is a function without parameters returning a string. You can also see that the implementation returns an instance of that function. And in the implementation of it, it references the captured value. And that's what I call a closure in this context, because the captured value does not flow into the parameterless function that is the return value. It flows into the function that generates the parameterless function. It's basically captured in that function and available as a closure. And in the example function, you can see how that would be used in practice. So first, we call this capture value function with passing it some explicit value, in this case a string. The return value will be a function without parameters, returning a string. And at the left-hand side of the expression, you can see that we assign it to some variable, which is called HOF, for higher order function in this case. Go is smart enough, the Go compiler is smart enough to detect the return type automatically, so you do not have to put type constraints or type information on this HOF function. That's automatic. In the next line, in the print line, we actually call that function and prints out what we expect to have captured that function, that input parameter. So there are also parts of Go that it would be nice to have these parts in the Go language. First of all, it's immutable data types. I said before that mutable data types is one of my favorites, and we should try to make data as immutable as possible. Unfortunately, in Go, there's no way to enforce that. The FPGo library in its implementation makes sure it never does mutation or it never changes data structures. It will always create copies of data structures hopefully in an efficient way, but it will never change data structures. So, but that is only by contract. There's no way to enforce that. It would be nice to have this in the language, but there is no const keyword. There's actually no way to do this. It would also be helpful to have type parameters for methods. This comes a bit out of the blue here because I have not introduced, and just take this at the moment as a statement. I've shown how type parameters work on functions. In Go, we can also have functions that are associated with data structures, very similar to methods on an object, but it's not possible to give these associated functions their own type parameters. Type parameters can only always be on either on the object itself or on standalone functions, but not on associated functions. In some cases, it would be helpful to have that. Maybe it comes one day. Function overloading is also not possible. We'll see the effect of that. So with function overloading, I mean having a function with the same name, but a varying set of parameters. And if you have a look at the composition functions, pipe and flow, we have to work around this limitation. Another limitation is the lack of type variance. So you know that in some type systems, you can specify whether a type constraint is covariant, contravariant, or invariant. So whether you can pass in a subtype, whether you can return a subtype, or whether the type we're talking about has exactly to be the type as specified. When dealing with generics in Go, generics are by design in Go invariant. So you cannot define co or contravariance. This also has causes some limitations, but it's still possible to use this to a good extent. It would just be easier in some cases if you could specify the variance of types. The other aspect is tuples. I'll skip this here a little bit in the interest of time, and we talk about this when we talk about error handling in Go, and then we discuss the tuple aspects. And the larger missing feature is hierarchy types. So generics, the current type system in Go only allows you to define types in one level. You cannot define a generic type that in turn is typed by another generic type. Again, we see an example when this would be helpful. This leads to the appearance of variations of some of the functions, of explicit variations of some of the functions for the different monads that this library has to offer, instead of exposing the same functionality just as one single function using higher kind of types. Internally, I've tried to implement this still in a way that the actual implementation code is not duplicated, but basically the facade that makes this usable has a duplication across the monads because of the lack of higher kind of types. Okay, so this is just my summary slide on why does it make sense to create a library such as FBGO for Go. Because the introduction of functional patterns motivate and encourage the creation of pure function or functions that can be well tested. Again, it's possible to do the same using imperative style, but following certain functional programming patterns just make it more obvious and more easy to follow that style that leads to testable code. Same goes for the aspect of making side effects, of being able to tell side effects apart from pure functions, and by contract, the immutability of data structures. Also, by having a rich set of composition functions, I believe we can reduce the boilerplate in our code, which leads to less mental complexity when trying to follow the code, because you basically can follow the code line by line. And since it's always using the same composition functions, it's easier to read. Using monads such as, we will see that, such as option, for example, avoids nested if-else statements, which again, in my eyes, reduces complexity. So in the second part, let's step into the FBGO library and see how this looks like in practice and in reality. So this slide summarizes a bit the different concepts that FBGO has to offer. First, I would say it offers a comprehensive set of functions such as filter, map, filter, reduce, chain, flatten, and I have a more complete list on one of the other slides, but it's a list of common functions across different data types. Right? And you might recognize these are some of the functions that are used in monads. So the implementation tries to come up with a set of monads and implements the same functions across them. So when looking at the code, no matter what data structure you're looking at, you will see the same composition functions, and you can rely upon the fact that these functions exist across the board. Like, for example, we have these functions, of course, for built-in data types such as slices, which are the concept of arrays in Go, slices and maps, which are records in Go. But we also have them for data types that this library introduces, such as the I/O data types, either option, readers, whatsoever. So for every data type, you find a common set of recognizable functions. The library also offers composition functions, so functions that allow you to stick together these map, filter, reduce, chain, whatsoever, these monadic functions in a chain of operations. And we have two of these composition functions, the pipe and the flow function, with the difference that the pipe function takes a value and then a set of operation and returns a value, and the flow function does not take an initial value, but just a sequence of operations, and it returns a new function that takes the initial value, and which is very helpful to writing point-free style code. And some of the monads that this library implements is the either monad for error handling, the optional monad for optional values. We have the I/O monad for representation of managed side effects and variations of that, like IO either, IO option, so like all combinations. And we have a reader abstraction where a reader is a data structure that takes a context and then operates on top of that context. And then this also exists in its different variations, like for side effectful operations, we have reader.io. For side effectful operations that can fail, we have IO, reader.io, either, and so on. And again, it's a consistent set of operations across all of these data types. The library also supports abstractions and concrete implementations of different monoids and semigroups. So monoids are data structures that carry an operation that can combine two values of the same type. And that's a semigroup, and a monoid adds to that concept an initial value, a zero value. And this concept is very helpful, for example, in the reduce case, where we want to apply a sequence of operations to a set of homogeneous values in a sequence. Supporting the claim that the library supports immutable data structures, it also contains an incomplete implementation of functional optics, such as lenses, prisms, traversals, which help you to work on immutable data structures. We have an HTTP module, which is a wrapper around the built-in one, and an interesting aspect, hopefully, to concurrency, which I will delve on in a minute. So how would you use the library? The library is available at the URL you see at the top here. Installation is really simple. You start with your new Go project, or maybe with an existing one. If you want to use a new one, you do a Go mod init, and just a Go get of the library, and then you have it installed. During this presentation, I will use some notation in order to consume that library, and you can see this sort of in the bottom here. In Go, you use the import statement to import libraries, like the format one, or in the lower lines, you see the import of the Go library, of the FP-Go library. And I'm typically assigning a shortcut to such an import statement. And you can see the shortcut A for the array import and F for function, as an example. Some may like it, some may not like it, but that is my preferred style, and I'm using this in the following examples here. So let's have a look at how the code looks like. Let's start at the right-hand side with a map the sample map implementation. So I have the same code both in idiomatic Go and in functional Go. You see the idiomatic part. In order to map each value of an array using a function in idiomatic Go, first we have to create the result array using a make statement. Then we would, via a range iterator, iterate over the input and fill the result array, and then print the result. Using the functional style, we can use the a.map function, which internally does the very same thing. The important part here is you pass the map function, the transformation function, and what you get back is another function that you can apply on your input. That's what you can see by the fact that the map function does not take two parameters. It takes one parameter and applies its result on the input. Reason for that is composability, as you can see in the next slide. From my perspective, it's easier to read. The use of the map abstraction is easier to read in this case because it does not confront you with the details of how exactly you would have to iterate over your source data structure. This is abstracted away, and if you understand what map does conceptually, you will also be able to understand what this line of code is doing. At the left-hand side, we see another example of the reduce function. It follows the same concept. In the first part, a reduce function takes a function that combines two subsequent values and a start value. So in the first case, we use the concat function of the sum monoid, which is just the plus operation, and we start with the value of 0, and reduce then computes the sum over all integers. We can also make use of the feature of a monoid that it not only carries the like the concat operation, but also the start value by using a fold operation, which in this case takes the monoid itself, and it can imply the concat function and the start value from it and apply it to the input feature values. So this is an overview of the set of monadic operations that's available. It's not 100% complete, but it gives you an idea. So we have the typical function you will find in a monad. We have the off function that creates a higher kind of type, map function, chain function. I've chosen the term chain in favor of bind or flat map, as you can find it in other languages, because as mentioned in the very beginning, this is very influenced by FPTS, and the FPTS library also used the chain function, or the name chain for the flat map or the bind operation. But logically, it's just a flat map. We have an apply function, flatten, reduce, so you might be familiar with many of these functions. And we have composition functions that allow you to write code in a flow, pipe and flow. And here we see a consequence of the lack of function overloading. Unfortunately, we have to create functions that carry the number of parameters they are taking in their name, because we cannot overload them. This is why we have like the pipe n, flow n function. Like in practice, it's pipe 1, pipe 2, and so on. So you have to specify how many arguments the function is taking to tell them apart. This is how this would look like. Yeah.
Yeah, you have 10 minutes to set to.
Okay, so let me speed up a bit, and then maybe.
Please go on with your slides anyway. Just if it's
possible.
Yeah,
I have.
We'll go through your presentation totally anyway, but please just speed up a bit. Thanks.
I will speed up a bit. Okay, thank you. All right, so this illustrates the use of function composition. In the left-hand side, we can see that we have a sequence of a filter and a map operation. And now it also makes sense why these operations return functions and not take two parameters, because by returning higher order functions, we can easily compose them in such a flow. So when we read this program, we can start with the input value. The next step will be a filter operation, a map operation, and we can easily understand what's happening in this piece of code. We're just following the composition. We can also do the same without specifying the input value, which you can see at the right-hand side. And this is interesting for point freestyle, where we try to write functions that do not have to explicitly specify a name of an input variable. And it's basically just replacing a pipe function by a flow function and removing the first parameter. In this case, the result of the flow will be another function that takes the same input as the first operator and returns the same output as the last operator. Quick word about immutability. Go does not have a way to enforce immutability, but there are some interesting aspects in Go that we can use. First, if you write getters and setters on functions, Go is a way to pass objects or structures by copy, as you can see in this example. So if you write an associated function, like a getter for a particular field on a structure, on a data structure, in this case, the get name, and we pass the struct itself as not as a pointer, but as the object itself, then Go will create a copy, and by modifying that copy, we are not modifying the original value. So this is already a good way to be able to work with immutable data structures. But sometimes data structures are just too deep and you don't want to create a full copy. In this case, the optics implementation of the FBGO library helps out. The optics implementation can create lenses and modifiers on lenses on data structures, and the implementation makes sure to only copy those portions of the data structure that are really modified by a lens or an optional or whatever optics concept we use. As an example here, we have the same person data structure as before. We use the L for lens dot modify operation with a callback that increments a value, in this case the age, and the implementation makes sure to copy the relevant parts of the data structure and return the correct value. Right. Let me skip this example in the interest of time, because I would definitely want to talk about error handling. Errors in Go are represented using an error interface. And what's nice in Go, or what's one feature in Go, errors are always handled explicitly, never as exceptions. So a function that can error out returns a data structure, and it basically returns a multi-value return value with the actual data type and an error object. And the caller is supposed to handle this in every single case, typically via an if-else statement. In FBGO, this is where we deviate from the idiomatic Go style, because in FBGO, we represent errors via an either data structure with this E, which is either an error or the actual value. And then we use the composition functions like map, filter, compose, chain, whatever, to handle these errors instead of doing this via if-else statements. An example can be seen here. In the top example, you can see this make URL function, which does a sequence of operations. It converts like a string to an integer, then validates that the integer is a port number, so it's positive basically, and then it formats it as a string. And you can see we can use the flow operation and just chain one operation after the other by using the standard chain and map operations and the flow operator without explicit error handling. In idiomatic Go style, every equivalent operation would return the value and an explicit error object, and you would have to check for the error object explicitly and bail out at that time. And bail out at that time. Since one of the goals of this library is to be able to integrate into existing ecosystems, it's also very important that the library offers a way to switch between worlds, I would say, switch between the functional world and the imperative or the idiomatic Go world. And for the places where we deviate, in particular for error handling, there exist conversion functions that convert idiomatic Go functions that return like a multi-return value of value and error into a function that returns an either, or equivalently functions that return value and a Boolean, which is Go's concept to deal with optional values, into an option object in Go, and vice versa. So it's relatively easy to use existing functions and also to expose functions written using the FBGO library as functions to the idiomatic Go world. Right, so I'm running a bit short, but I would definitely want to talk about managed side effects, if that's possible. In the FBGO library, and we were trying to tell functions that have side effects apart from functions that do not have side effects by introducing the IO type. The IO type is just a function that does not have any input, but that returns an output. And the idea is that this makes it very clear that this must be a function with a side effect, because how else, other than the trivial constant function, can a function return a sensible output if it does not have any input? This can only be true if the function has some side effects, such as reading from a database, a file, or making an HTTP call. And already by having this data structure plus all of the monadic operations on this data structure, we can easily separate out pure functions from side effectful functions. A quick example is here. This is an example that reads a number of files. And you can see the IOE prefix here stands for IO either. Again, we have the same composition functions, map, chain, to handle composition of the composition of operations. And in this very example, we are reading like a text file, a JSON file, and then we are combining these files to a result type. And one of the interesting parts here is this sequence operation, the sequence T2, 2, because we have this numbering problem because of the lack of function overloading. T stands for tuple. And the sequence operation actually makes sure to operate the input operations like as in a unit. Let's put it that way. The default implementation is for I/O operations to run the input I/O operations concurrently, because Go has such a powerful concurrency concept, and it makes a lot of sense to run I/O operations concurrently from performance reasons. It is also possible to run I/O operations in parallel, not in parallel, sequentially, if that's desired, but the default implementation is concurrent. So this makes it really easy to come up with a system that scales well across I/O operations, because concurrent I/O for these I/O monads is actually built into the library. Right, I skipped this in the interest of time. So for this, a final word on performance considerations. The primitive operations such as map on arrays have a very similar performance characteristic compared to native implementation in Go. So this shows a performance benchmark for a map operation on an array compared to the idiomatic operation. It's basically identical from a performance. In case we have more complex operations, it turns out that the fact that the FBGO library returns higher order functions can have a negative side effect on performance if you measure performance on the micro scale. So if the actual operation that implements your business logic is extremely fast, then there can be an overhead of composing functions using FBGO. And as an example, I have here in the top a map and filter operation. The sample code is actually in the open source project for this. With a filter predicate that is very fast, just an is-even operation. In that case, the idiomatic implementation is much faster. But in case the actual filter predicate is a bit slower, such as checking if an integer is a prime and not just if it's even, then it doesn't really play a role. The fact that idiomatic seems to be faster, idiomatic is still a bit faster, but no, it's just vice versa. Sorry, that it seems that functional is faster in this case, but that's, I would say, an artifact of my benchmark. It just doesn't play a role in this case. And since many operations in real world are really bound by I/O operations, so or business operations that are not that fast, the overhead that this library introduces is, in my experience, acceptable, because it is visible on a micro scale, but not on a macro scale. And of course, it really shines if it comes to executing operations, I/O operations, because per default, it does this sequential concurrently. And of course, here I have another benchmark, of course, tailored to show that example. Doing a sequential operation is, of course, much slower than doing it concurrently. But since it's so easy to implement it concurrently using the FPGO library, using I/O operations, I would say that's one of the major advantages of using these patterns. This, in fact, actually concludes my presentation. I'm sorry for running over a bit. You can find examples, all examples I was showing here, also in the open source project in the given link, plus many more. I've also converted the examples of Professor Frisbee's Mostly Adequate Guide to Functional Programming, which is a fun read actually to FPGO. So you can follow that book and compare how it looks like in FPGO. And since it's so similar to FPTS, many of the tutorials you find for FPTS also apply to FPGO. So with this slide of references, I would conclude my presentation, and thanks a lot for listening. And maybe we have a minute or two for questions, and then I would hand over.
Thank you very much, Carsten. Very interesting. It was a very good presentation and very cool with this. Like, first that you shared your like personal journey in and also all the problems you run into and lessons learned from imperative programming, and then also very interesting the presentation or the graphs you showed around the performance consideration. That's also, I think, very interesting, because using different strategies and different techniques when you're solving different problems. That's very interesting. Yeah,
Absolutely. I wanted to point out it's so this library, I think it's very good to go to implement functional styles to Go, but it's potentially not a solution for everything. As you can see, if you're into micro benchmarks, then maybe this is not what you want to use.
Yeah, we have one question from the chat. Do you know any plans of making FP in Go lighter, like a lightweight FP Go?
To understand that question, I would have to understand what makes it heavyweight in the first place. I would say, yeah, please share your thoughts about why you think it's heavyweight with me. You can use that. You can just use fractions of that library. If, for example, if you don't buy into the concept of error handling in ethers, you don't have to use this. The compiler makes sure to only include the portions you need. It's not that tightly integrated. But if you, for example, want to use the map reduce functions on slices or other helpful functions, you can use just the portions of the library you need.
Yes. Cool. Good. Thanks. There's no more questions in the chat. People are just saying thank you very much for your presentation. Also, some people are saying, I wished I had this library when I was writing Go. So
give it a try and let me know and get in contact.
Yes.
Thank you.
Thank you very much, Carsten. And we'll put out all the reference below in the below in the comments later under the presentations. Anyone can find all the good references you've given, and also the reference to your to the library, to the FPGO library, so people find it. Yes. With that, thank you again very much, Carsten.